Hey everybody, it's Ribley back again. We're going to talk about triple integrals with spherical coordinates today. Probably my favorite of all of the triple integrals. They're going to freak you out at first. I'm not going to lie to you. But that's okay. You're going to be fine. I promise. What we're dealing with the triple integral in spherical coordinates is instead of, if you recall from cylindrical coordinates, it was like we were taking a slice of a cylinder and then we were sending that off to some function somewhere else. What we're doing now is we're taking a slice of a sphere. Now, this will not work for all functions. Please understand that. But when they do look like you're taking a chunk off of a sphere, and I love this diagram, it's so nice, then spherical coordinates are so much easier to work with than traditional rectangular coordinates and polar, because the problem with polar is you have a z that comes up off the xy plane. So it basically takes that chunk of the cylinder and it rises it vertically. Well, if we've got any curvature to that movement, we can run ourselves into trouble pretty easily, and that gets really, really confusing, and it muddles down the integral itself. So let me say this. We're going to come up with a set of rules. Okay, we're going to cut very much like polar. I'm going to start with the polars just so we have it. We know that r squared is equal to x squared plus y squared. And I know that x equals r cos theta. I'm not even going to bother with the tan one. We won't need it. Y equals r sine theta. And then for polar, we had z equals z. Okay. Now, in this case, instead of r, the problem with r is it's locked into a plane, right? Because it carves out a little slice of a cylinder. It can't bend it all up off of that plane. So what mathematicians said, well, what if I want to bend it? What if I want to take this radius, and instead of having this radius be pinned to a plane, regardless of which plane that is, what if I want to have it, say, stick out from the origin, almost like a vector? Think of it like a vector. Now we have a new angle, okay? With r, we had an angle theta. Now this new radius, we're going to say, this new radius is going to have an angle against the against the z-axis as opposed to the x-axis. And its name is rho. All right, now think sphere. We know the equation of a sphere. I'm going to have my first piece of new information. I know that rho squared is equal to x squared plus y squared plus z squared by virtue of the fact that it's on a sphere, right? It's on a sphere centered at the origin, which makes it really handy. Now I got to get a little bit crafty because all I've got are these things, okay? So here we go. What I'm going to have is, does everybody agree that if this is r, then this guy is r? So what I need is a relationship between x and y and r and theta and this new rho and this new angle phi. Okay? So if there's an r up here, I can't draw on this because I'm not on my machine. But we're not going to worry about it. Hopefully everybody sees that opposite over hypotenuse is going to be sine, right? We know so. So I know that the sine of phi is equal to, now the opposite side is this r, right? So it's going to be r over rho. Now look at this. I instantly have a way to get between r and phi and rho. So I know that this implies that r is equal to rho sine of phi. Ta-da! And there's nothing to it. That's the best part. Now, don't get too crazy yet, because it's gonna get nutty before it gets unnutty. But this is my bridge between polar and cylindrical, which is great because now I've got x is equal to rho sine of phi times cosine of theta. Right? All I'm doing is sticking a rho sine phi in wherever I see an r. Y is equal to a rho sine of phi. That's terrible. Cosine of theta. And now we have this awesome x squared plus y squared plus z squared equals r squared, right? Or excuse me, equals rho squared. Other than that, oh, I do have to account for z. Remember before, z was just z when I was talking about polars. This guy right here. But what's z? Well, that's this distance here, which is also this distance here. So you can tell this is, here's rho, here's phi, and here's the adjacent side. Well, I know that cosine of phi is equal to z, that's the vertical distance up to this point that's just kind of hanging out in space that rho goes out to, again, think like a vector, is equal to z over rho, which implies what? Well, rho cos phi is equal to z. And now I have everything that I need. Now, again, think of these as being very, very specific for what we need, okay? But they're also really, really powerful. When you need them, they are fabulous to use, okay? And I'm going to make the adjustment here in just a sec. Just like the triple integrals that we had when we were dealing with cylindrical coordinates. Let's see, what was the formula again? Okay, the formula was the integral, or excuse me, the triple integral over the enclosure of f of r cos theta, that's x, right? R sine theta, that's y, and then z, right? And then we ended up with the delta v, which ended up being what? R, dz, dr, and d theta. Now, this guy here constituted that delta v, all right? Now, this one's going to be a little bit trickier, but don't panic. And this, I'm telling you, it's a blast. So this was for cylinders. I just say for polars, right? We use polars, but it's definitely for cylindrical coordinates for triple integrals. I'm going to have a triple integral over the enclosure. It's going to be f. Now, instead of these guys, what I'm going to need to put in, it's going to be f of rho sine phi cos theta. See, all I'm doing is sticking a rho sine phi in wherever I see an r. Rho, and this is the way that we translate x, y's, and z's into this guy. This is going to be rho sine phi. I have a terrible time with phi, sorry guys. Sine theta. And then what was z? Well, it's sitting right here. We just discovered it. Rho cos theta. Right? Now it's no longer a z because, remember, this is part of a cylinder. And then, of course, we're going to have that delta v. Now, the delta v here is going to be the trickiest part because everything else is just plugging in a bunch of values. So where does delta v come from? Well, the thing we have to remember is since these are cylindrical, now what we have, excuse me, what we have are, I'm going to finish writing that, what we have are arc lengths. They're not lines. We don't approximate them with lines. We approximate them with arc lengths. Remember way back when we were doing double integrals with polars? Well, we're going to deal with that same issue here. But watch how this works. What we end up with, excuse me, I'm sorry, I got something chomping in my throat. What we end up with is, first things first, we're going to have delta rho. All right, so this is a V, by the way, not an R. I'm going to have change in rho, because rho changes linearly. I'm going to have change in rho. That takes care of that one dimension. Now, what's this curve right here, which is hard to see? How is this thing created? Well, it's created by swooping rho around theta. Well, we know that an arc length, right? Now, they did a bad job in this picture of actually showing this rate of change of R, not of R, but of theta, but it swooshes out this arc length. And we know from pre-calc that S is equal to R theta, right? Well, in that case, what we have is we're going to have times rho times delta, oh, I'm sorry, not times rho. We're going to have rho, whoa, oh, I forget this thing doesn't have an eraser. Excuse me. What we've got is, the way that I just did that, is this swooshing out of this little arc length right here is what? Well, it's R, and then it's this d theta. So that R we now know is rho sine phi, so rho sine of phi, and then times delta theta. You're probably seeing where this is going. So that swoops out this arc, which translates to kind of this arc here. Now I got to swoosh out this arc right here. Well, what's that created from? That's created from phi coming down off of the z-axis, right? So what do I have? I'm going to have a rho. Again, S equals R theta. It's pre-calc. You've seen it. R in this case is rho. And then my delta phi creates what I've got, right? So this is going to be, what did I say? This is going to be rho and then delta phi. So what does that give me for this chunk right here? Well, multiply them together. I end up with rho squared sine of phi times delta rho, delta theta, and delta phi. And that's it. So when I rewrite this guy, I end up with the triple integral over the enclosure, and we're going to have a little bit of fun. These are tricky. I'm not just going to say, okay, here's the theory behind it, and off we go. I'm going to do a couple problems with you. They're not going to take very long, but I want to make sure, because this is kind of out there, this can get kind of crazy, that you can sort of visualize what's going on. So I've got, what do I have? I've got f of x, which we know is rho sine phi, which is r. Sorry, you guys. I'm having a hard time with Jimmy's pen. This is rho sine phi cos theta. That's x. And then we've got rho sine phi sine theta. And then we know that z was equal to what? Rho cos phi, right? Cos phi. And then I'm going to run out of space, so I'm going to just kind of bring it down here, so bear with me. My volume is created by rho squared sine phi, and then d, what did I say? D rho, d theta, d phi. And that's it. Now, hopefully you realize already that if this guy right here is gone, if this is a 1, then I can find the volume of the thing that I'm looking at. It's just volume. So if I want the volume over the enclosure, that is simply equal to the triple integral over the enclosure of rho squared sine phi, and then d rho, d theta, d phi. And I can mix and match these things around. We know that, right? For beanies and all of our other little properties that are so useful. Okay, so I'm going to do 2 problems with you. All right, because I want you to have your brain wrapped around this just a little bit. All right, so these are now officially examples. Okay, example number 1 is this. What we're going to do is I'm going to write an integral, and we're going to sketch the solid. So I'm going from 0 to pi halves right here. Oh, excuse me, let's go 0 to pi 6. I'm actually using a problem out of the textbook, which is a pretty good problem. So 0 to pi 6ths right here. I'm going from 0 to pi halves. That's where I got screwed up. Pi halves, and then I'm going from 0 to 3. 0 to 3, and then I have rho squared sine phi d rho d theta d phi. Now, we're not going to evaluate it, not at all. We could easily evaluate it if we wanted to, but we're not going to. All that I want you to do is I want you to try and visualize what's going on with this thing really quickly. So everything appears to be kind of first quadrant stuff, right? So here's x, here's y, and then here's z. Now, what's happening? Well, I've got this rho, and rho is going to come away from the origin 3 units, okay? So let's start there. I'm not going to draw it. I'm just going to kind of dot it. So I'm just going to come away 3 units, and this guy is going to lie in the xz plane, okay? Now, that's a little bit too much, and here's why. I have to be respectful of that phi. So you kind of have to do 2 things at once. Where is rho? Well, it's 3 units away, but it makes an angle with z of pi 6. So I'm going to put it, pi 6 is 30 degrees. I know this is a little bit bigger than 30 degrees, so bear with me, would you please? His thing doesn't work the same way that mine does. All right? And then what am I going to do? So this angle in here is pi 6, right? Let's change colors just so we can kind of see what's going on. Now, it's going from 0 to 3, so this thing is carving all the way up. Now, think about it, it's moved away from z, and then what's it going to do? Well, it's going to wrap through 90 degrees, right? Does that make sense? Now, it's part of a sphere, so we got to remember that. It's carving down 360 degrees, and then it's carving around 90 degrees. So what I have is, if you can visualize it with my absolutely horrific drawing, is you got yourself a little ice cream cone. Isn't that beautiful? That's what it looks like. Now you may say, wait, Ripley, how are you getting the cone part of the ice cream cone? How's that happening? Well, because rho goes from 0 to 3, right? True. And then what I do is I carve that sucker down to pi 6, that's this angle right in here, and then I wrap the thing through 90 degrees, and I end up with this little, you know what, that's a bad drawing, because I'm only ending up with a quarter of that ice cream cone, right? I would have to go a full 360 to get the entirety of the ice cream cone. I'm sorry about my horrible drawing. So let's see if I can visualize this thing a little bit better for you guys. Here's my z-axis. This thing's coming out this way and out this way. It's carving. We got 360 degrees. Oh, this is just going to be a train wreck, isn't it? I'm so sorry. And remember, it's rounded at the top. So how do I draw it? I am such a horrible drawer when it comes to trying to get these things done. Like that. So this would actually be all the way up to 3 up here. I just drew it so badly. I'm so sorry. But can you see what I'm saying? It's a quarter. It's a quarter of an ice cream scoop. All right. Now, again, I apologize for my gravity. Okay. So that's what it's going to look like, only rounded at, yeah, I'm such a poor drawer that it's hard to do it. Okay? So you got to sort of be able to visualize these things as they happen, because it's happening simultaneously. You're going from 0 to 3, then you're taking that thing and you're cranking it down, and as soon as you do that, you create area, right? That area, I can at least draw that. So here's Z. Here's my z-axis. I go up to 3, and then I crank that thing down 30 degrees. So what I'm creating is, it's kind of like opening up a fan, isn't it? I'm creating this little pie-shaped thing. Now, very much like what we did with rotational volumes back in Calc 2, I then open that thing through 90 degrees. Ooh, I think I'm getting there. And I end up with that little ice cream scoop thing that I'm talking about. And that's where that comes from. It's a quarter of an ice cream scoop. All right, I've beat the heck out of this problem. I apologize for my lack of ability. Now, I want to do another one. What I've got is I have a triple integral. I have triple integral over and enclosed. Now, this one's going to be different. I think you'll like this. I've got a triple integral, only now I've got x squared plus y squared, right? And I've got dv, and it says where E lies between, this is just between x squared plus y squared plus y squared plus z squared equals 4, and x squared plus y squared plus z squared equals 9. Now, take a minute. Ignore this function for just a sec. Just ignore it. All right? Just forget about it. What are we talking about? Because all we're gonna do is translate these into spherical coordinates. But what I want to know is, I want to know if E is defined as lying between those two things, then what is it? Well, hopefully you see that they're both spheres. This is a sphere of radius 4. This is a sphere of radius 9. So if I were to draw a sphere, hopefully better than I can draw anything else, because I can put on my units later. Oh, God, I'm just awful. Sorry. And then I would have a bigger sphere, like that. You guys can hate on me all you want, by the way, because I'm really a poor artist. I shouldn't be this bad. What I'm talking about is the volume in between those two spheres. That's all I'm talking about, right? If this has a radius of 3 and the other guy has a radius of 2, I'm talking about the volume in between the two of them. Now, we've got some work to do if that's the case, all right? Because what we're going to have to do is we're going to have to set up this integral so that it looks pretty. That's what we got to do. So first things first, we're going to do this, and remember, we work our way inside out. Now, let's keep it simple, because I always know I'm going to have a rho squared sine phi, and then I'm going to have a d rho, d theta, d phi sitting out here. We want to be as clean with this as we possibly can. Now, if I'm going to make a sphere of radius 4, that's pretty, or excuse me, of radius 2, that's pretty easy. I would just have rho go from 0 to 2, right? And then I would go what? Where would phi be? I'm going to build this sphere. I go up to rho goes up to 2, and then I would need to carve through 180 degrees, right? Not 360. Because think about it, again, like one of those Halloween decorations that you store flat and then you open them up. Again, this is very akin to what we did for rotational volumes back in Calc 2. I only need to get halfway around the circle because d theta is going to take care of the full 360 degrees, right? But I'm not talking about just that. That would be easy to build. I'm talking about the volume between them. So the volume I'm looking for, to use a Ripleyism, I'm looking for the action in between these two guys, right? That's what I'm looking for. So where does rho go from and to? Well, its inner boundary is the sphere of radius 2, and its outer boundary is the sphere of radius 3, which means rho goes from 2 to 3. That takes care of the betweenness. Now, to build all that volume out, it's exactly the same. I know that theta goes from 0 to 2 pi, because I have to curve this thing through 360 degrees, and I know that phi goes from 0 to pi. That's it. Now, the only job left to do is deal with this x squared plus y squared. Well, we can do some light lifting with this because I know from polar that x squared plus y squared is equal to what? R squared. So guess what? We know that R is, since R equals rho sine of phi, I can simply rewrite this as, since it's R squared, it's going to be rho squared sine squared phi. If I wanted to rewrite this, it would be rho to the 4th sine cubed phi, and then we're just off to the races. We do what we do. We use our techniques of integration. All right? Now, I know that might have been a little bit confusing, but it's a couple of problems. It's dealing with spherical coordinates, but it's coming at them from different directions. Hey, here's my integral. What's it look like? Versus, here's this integral, and I'm bounded by these regions. How do I write it? Or not that, well, yeah, how do I write it as an integral that I can actually take the integral of? Okay? So, that's about it. We're going to do a whole bunch of these. We spend 2 days. Like I said, this is my favorite section. Really, all of this is my favorite chapter. It's such a fun chapter. I hope you guys are enjoying it as well. And it's the last section in the chapter. You basically, at this point, you should at least have some familiarity with all of the techniques of multiple integration. I'm looking forward to doing a bunch of integration with you guys tomorrow in class. Again, I apologize for the technical difficulties. Hopefully, we'll have those resolved by next chapter, but I wouldn't count on it. Don't bet on it. All right. Have a wonderful day, and I will see you tomorrow.